Okay, welcome everyone. Great to see this turnout. Welcome to this week's CDAC webinar talk. It's a great pleasure to introduce one of our close colleagues, Professor Roald Hoffmann, whom I'm sure is well known to most of you. As one of the leading theoretical chemists and a career spanning many decades, it's difficult to do justice to Roald's many contributions in an introduction like this. He's contributed to our understanding of chemical bonding over the years, beginning with his work on the conservation of orbital symmetry, for which he received the Nobel Prize in 1981. And since then, Roald's contributed to many areas of chemistry beyond that and other areas of science as a whole, as well as to literature through his many articles, books, poems, and plays, consistent with his title of Frank Rhodes Professor of Humane Letters, a position that he's held at Cornell for a number of years. In the mid-2000s, Roald turned his attention to understanding structure and bonding in molecules and materials under pressure, or molecules in distress, which was the title of one of his articles back then. This work, and much of it done with Neil Ashcroft, who's also joined us, has helped guide our thinking about a wide range of chemical and physical phenomena being uncovered in experiments on materials in extreme conditions, from carbon nanothreads to room temperature superconductivity and hydrides, just to name a few examples. So it's a pleasure today that Roald's going to share with us, I hope, some of his current thoughts on connections between bonding at 1 atmosphere and elevated pressures. So Roald, thanks very much for agreeing to give this talk.
Good. Well, I'm glad to be here. As you can expect if you know me, I'm speaking up for chemistry in this meeting ground of chemistry and physics that high pressure science represents. And the particular experience I want to encourage you to draw on is simply that chemists in 200 years of frenetic activity have made about 100,000 reasonably well-characterized molecules and solids, sometimes not so well characterized, and sometimes difficult to tell. Your DNA is a molecule, my DNA is a different molecule. Of those 100 million molecules, about 1 million have had their X-ray structure done, and a few hundred their neutron structures. So there is a lot of information about structure and also elsewhere about properties that one should draw on as one extrapolates to higher pressure. Let me talk a little bit and structure the talk in terms of this little diagram I've borrowed from Tianguez and Eva's paper here, which shows the typical flow of a calculation. I'm having trouble in moving. There is a crystal structure prediction of some sort of stable and metastable minima, a structure search. There is a convex hull about which I'll have more to say that's generated that looks at the stability. Structures come out, and then from those one does the electronic structure calculation here, a density of states, and then an estimate of conductivity, of superconductivity, if one is interested in that. Now, let's see, I'm having trouble advancing this, so let me just figure out how I can do this. Here we go. Here are two typical convex hulls of this type. At left, from Oganov's work, it's on tungsten borides at under 1 atmosphere, and to write from one of the first papers we did, in which we used one of these diagrams, in which we looked at lithium hydrogen compounds and found that at high pressure there were also stable points for LiH2 and for LiH6. And you see also lots of metastable minima. So these were local minima that were stable to small distortions, but were thermodynamically not stable with respect to decomposition to the elements plus one of the compounds on the convex hull. One of the questions is, should we pay any attention to the metastable structures? That is, the things that are connected by the dot, or the many points that you see in a diagram at left, which are either circles or X's, which are individual structures that were computed. And a connected question is whether in the experiments, in a typical situation, in a high pressure experiment, whether equilibrium is reached. Now, the problems are manifold in whether equilibrium is reached. People heat things, usually indiscriminately with a laser for a time which is of the order, let's say, of seconds. We are dealing here in question of reaching equilibrium with a very basic slide 0 of a chemical engineering curriculum. You need mixing or access on the more or less one hopes molecular scale, but one is really dealing with nanoparticles most of the time. And one needs mass transport. And solids, which we are fated to use in the high pressure experiments because everything solidifies eventually, or almost everything. There are some interesting exceptions. Everything solidifies, and that is not good for mixing. And it's very good for mass transport. Incidentally, this slide just shows why the chemical industry wants to work with liquids. They have good mixing and they have good mass transport. Both gases and solids are a real problem for synthesizing things. I'll tell you in the first of my controversial, perhaps, and also critical evaluations, I have assembled here 3 representative slides around lanthanum H10. At left is the first synthesis by Zulu and in Russ's group, and the measurement of the conductivity, which is so impressive with a 250 degree above that. In the middle, you see the later but independent study from the Erametz group by Drozdov et al. With its points. And at right, you see the paper that's up on archive from Hemley and Tozer groups with the spectacular heat treatment and the magnetic field and the rise in the conductivity. My observation as an outsider, though I'm a little bit connected to the first one of these, but basically I'm an outsider. My observation from seeing slightly or greatly different temperatures and seeing an honest story told of the 3 samples that are behind, let's say, each of these measurements, and also from seeing that they're made in different ways using different starting materials. My overall observation is I don't think equilibrium is reached in these things. Now, and people will disagree with me, but I think that the experimental evidence is not there for there being equilibrium. And all we have is 2 or 3 measurements. I want you to just remember how different this story is from the cuprate superconductors. When those were made, they were immediately made by 100 other people. There was no question about reproducibility or about equilibrium being reached. That was apparent. Now there is an interesting question. The question of whether equilibrium is reached, or the question of stability in general, is a question which we know is addressed both thermodynamically and kinetically in terms of things being stable, unstable, metastable, a thermodynamic statement of energy or enthalpy, if you like. But also there is a question of reactivity, and that is this activation energy that has to be passed by to stop any reaction, to prevent a reaction from happening, for allowing a reaction. There is an interesting difference between physicists and chemists. My general perception is, since I've lived in both communities, is that physicists do not see a barrier until a junior level physics course. Until then, they're dropping weights and accelerating things, and whereas the chemists see this barrier right from high school on. So there is an important thing. The other thing is that chemists all the time, when they make things, are concerned about reactivity and are concerned by the question, in the presence of what is something stable? And this will come up in another moment. If you want to read something for fun about this, about the thermodynamic sinks of this world, there is something I've written in American Scientist. We will distribute the recording of this will be available anyway, and you can get a reference to it. Not important. Things are pretty simple. All organic molecules, and that includes all in your body, will burn in the presence of oxygen with a very nice flame exothermically. And that is, people burn, and not just with passion. We are all thermodynamically metastable. Somehow people can sell diamonds, even to people doing experiments with diamonds. And for anyone who has seen a thermite reaction, which is the reaction of an iron oxide with aluminum, you will begin to wonder how people can cook in aluminum pots, which they do easily. The hydrogen balloon experiment, I couldn't quite get it right in here, but the hydrogen balloon experiment that all of you have seen, you know what's going to happen to that balloon when that flame touches it.
Is this yours?
Yeah.
They are yours?
That flame, when that flame touches that balloon, it's going to explode, driven by the 286 kilojoules per mole, that's 22.4 liters of the hydrogen, that'll set this off. But that's not the interesting thing about this reaction. And however, we focus on the explosion. The interesting thing about this is nothing will happen in that balloon without the flame. There is a barrier to that reaction. The barrier is not surpassable at room temperature. So that it's passing the barrier that makes metastable compounds, makes you think that metastable compounds are not going to survive. In fact, life is absolutely chock full at every step with metastable compounds. So what's the moral for people calculating those convex hulls? Don't throw away the things above the hull. They are also there. Another way that chemists see this, or at least theoretical chemists who really have a lot to learn in this business because they're particularly naive about chemical stability. Here is a homonuclear diatomic, so the first row and second row. The most stable diatomic to atomization is the nitrogen molecule. It takes 10 eV to knock apart a nitrogen molecule into 2 nitrogen atoms. The next most stable one is C2, the next one O2, The next one, P2 in the second row. Here are 4 molecules, each of which it takes more than 4 eV, around 5 eV or more, that they would gain that's the energy you'd need to put in to break them apart into atoms. So they are stable, but you haven't seen any bottles of C2 or P2. And you will never see a bottle of C2 or P2 because they are spontaneously polymerizing. We actually see C2, the blue color in hydrocarbon flames is due to an excited state of C2 emitting. But the diatomic molecules, even though they are stable by 5 eV to breaking apart, that's what it takes to break them apart. They are, in fact, very reactive. So just because you are stable does not mean that you're not reactive. That's the other lesson of chemistry. Another example, just to finish the story of simple examples, is H3+. H plus adds to H2, giving off 424 kilojoules, 4 eV in a process. That's the reaction, the heat of the reaction, H plus H2 to give H3+. The trihydrogen cation is probably the most abundant form of hydrogen in the universe, rather than H or H2. But it's probably H3+. It's a very stable molecule, but you have not only not seen any bottles of H3+, but also there are no molecules that are stable, that are complexes that bind H3+ in any way. The reason is it's easy to see what's happening. The H3+ is very exposed and very stable, but very reactive. So here is a table from Wikipedia of proton affinities. Proton affinity means the energy given off when the molecule in question reacts with H+. So the proton affinity of H2 is 424 kilojoules. I've circled that in red. The proton affinity of helium, of a helium atom, is 178 kilojoules, 2 eV. Hydrogen is 4 eV. Look down the table and you'll see that H2 is pretty close to the top of the table, except for O2, which has special reasons. The only things which want a proton more thermodynamically than H2 are the noble gas, are the only things that want a proton less are the noble gases. Everything else in the world will steal a proton from H3+ to give itself protonated. Look down, for instance, this list, for instance, for triethylamine. That's an amine, an ammonia. That has a proton affinity of almost 10 eV. If one of those amines encounters H3+, it's going to gain 6 eV by taking the proton away from H3+, from H2. So that just because H3+ is stable doesn't mean that it's going to be there. So the moral here is, please make no claims for commercial utility or even detection except in a cold noble gas matrix or in a near vacuum molecular beam. Make no claims for commercial utility based on metastability or even stability. I've just shown you stable molecules that are very reactive unless you have calculated the barriers around those minima. Claims for practical utility of metastable materials should be accomplished by barriers to transformation to some more stable variant of what it is, and also, if you really want to sell the stuff on Earth that you're making and you're claiming the cat's pajamas for the properties of some given material, you better calculate the barrier for its reaction with various components of the atmosphere, which are N2, O2, and the worst actor in the atmosphere is the little humidity we have. That is because water is both an acid and a base and very reactive. Research proposals and press releases are exempted from these guidelines. Okay, here is some references on metastability. The literature, the field of solid state physics and material searching is now quite aware of the problem of metastability and what needs to be done. Here are some leading papers, some of which I got from Eva Zurek. There are some crystal structure prediction methods, especially the one from Stefan Gödeker and Max Amsler, that are very good at, with a lot of work, at predicting the barriers around a minimum as well as the minimum. But it takes a lot of work. Anyway, the story on metastability is, don't worry about it. Do worry about metastable compounds. Don't pay attention only to stable compounds, but you have to at the same time worry about the reactivity of these things and don't make any claims about them. Metastable materials, that they're even local minima, do tell us a lot about the behavior of metal, of matter in general. I've found out a lot about molecules from carefully designed probing of metastability in molecules that don't exist for very long. There is another interesting question I will not get to, but maybe one day we can structure a discussion, and that is there some connection between metastability specifically and superconductivity? I don't have that yet, but it's something it's worth discussing. What I want to do now is to make some sense of the structures we see under extreme conditions with you, the structures that we have seen theoretically. One is the effect. What is the effect of temperature? I don't have time to talk about this much, but temperature, if applied under equilibrium conditions which allow you to achieve equilibrium, is important for overcoming any barriers. So it's very important for getting to the most stable if there is a global minimum structure available. But the way there is fraught. There is another interesting thing about high temperature, and that is, could there be some special reactivity channels that open up under high temperature? We don't have time to talk about that. The effect of pressure. First, some general principles that I want to go through with you. And the second one is some specific things that have to do with hydrides. The general principle is summarized in a simple phrase. When you apply pressure, the volume goes down. When the density goes up, if the number of particles is the same, the particles have to get closer together on average. There is no option to that. It's the only thing that happens under pressure. And so this could be the subway in Tokyo where people are hired. Here it's more particles in a given volume. So it's a little different thing, but basically it's the sardine can principle that is at work. The first thing that happens, we have written a paper where we, very close to the beginning, it's good to be an outsider. I was an outsider to high pressure. By being an outsider, you can see what's special about a field easier than if you're somehow always been working in it. And in the beginning, and encouraged mainly by Wojciech Krochala, who is now of course in an independent research position in Warsaw in Poland, we outlined a kind of hierarchy of responses to pressure in crystals in a paper in a chemical journal. And the first, these are not rules that A is followed by B, followed by C, by D. That would be too simple. The world is complicated. This is a set of sort of overlapping things that happens, which helps you to get oriented in this world. And the first thing, and especially prominent for molecules, is that you squeeze out the van der Waals space between molecules as you compress a molecule. Let me show this to you because there's no substitute for actually showing this. Let me get a pointer here. Okay, can you see my pointer? It's up at the top left there. So the two top drawings, Russ, can you see that?
Yes, we see it.
Okay, the two top drawings are for the calculated equilibrium structures of H2 in the molecular region before it goes monatomic. So that is under 400, 500 gigapascals. And this at right in the graph is the bonded HH distance in the diatomic. And you will see that it varies over about 2 or 3 hundredths of an angstrom as you go from hydrogen from phase 1 to phase 4 of hydrogen. The one at left is the next near, the second shortest HH distance. I'm going to point to one of these from one molecule to the next molecule, okay? That's the distance imposed by the van der Waals contact in solid hydrogen, for instance, at low temperatures. But look what happens to that. It follows a classical kind of equation of state curve, but the easiest thing to say about this, in the first 10 gigapascals of pressure, the first tenth of a million atmospheres that you apply, the distance between non-bonded hydrogens goes down by 1 angstrom. Not the trivial games that are being played by the bonded distance, so to speak, but you're squeezed out the space between molecules, but the molecules remain. This is illustrated below. This is silane, a calculation on silane over a range of pressures in a structure which has 2 molecules of SiH4 in a unit cell. And this is the distance between one green ball and the green ball in the next molecule. And that one you also see goes down in the first 10 gigapascals by 1 angstrom. The molecules are pushed closer together. I can't show you any clearer than that, how this happens. The next thing that happens as you squeeze is you must get closer together. The 2 molecules, let's imagine the 2 molecules squeezing. They're coming closer together. At some point, things that are attached to one molecule are getting close to the nucleus of the other molecule. And what you get is an increase of coordination. At main group and transition elements, you get an increasing dimensionality. Let me show it to you for silane again. Silane initially is a molecular crystal of SiH4 molecules like methane. At 100 gigapascals, we found a structure which is at right over here, where it has each silicon, one of these dodecahedra is stripped away. Each silicon has 8 hydrogens, which are shared with 8 other silicons. And so this is silicon H8, and then each of them is shared with 2 silicons. So the stoichiometry is SiH4, but this is now a three-dimensional array. It's no longer a simple molecule that you can recognize. Pickard and Needs found a structure slightly lower in enthalpy that also has 8 coordinate silicon, but now each silicon shares with 4 surrounding silicons 2 hydrogens each. You can see this diborane-like unit over here. So just think about this. You've got the same number of atoms. They're being shared more. They've got to be shared more with other elements. But you have the same number of electrons, just like you have the same number of atoms. So that the bonding must be multi-center, multi-electron bonding. We're actually used to this in chemistry, but in only one little part of chemistry at 1 atmosphere, and that is the chemistry of the boranes and electron deficient bonding. In general, as you apply the pressure, you move from molecules to higher dimensionality networks. And these are much harder to think about. Another thing that happens about pressure is, which I don't have time to talk about, is occasionally electrons get squeezed out from the region of the nuclei and into the small nooks and crannies between nuclear cores. And these are what a chemist would call electrides. There is some experience with these even at 1 atmosphere. They're pretty rare, but they occur for elements and compounds, and they are something to be watched for. I just wanted to, in closing this section, I just wanted to mention that there are ways actually that we have worked on to calculate these reaction profiles. You see this, the barrier, and then going down, to calculate these at elevated pressures. Here is a reference. It's a work with Bu Chen and a very good Italian theoretical chemist, Roberto Cami at University of Parma. And he has a method called the XPPCM, that stands for extreme pressure polarizable continuum model. So here is a reaction. It's called a molecule called cyclopentadiene reacts with an ethylene to give a molecule, a bicyclic molecule that you see here. The black line is the reaction profile at 1 atmosphere, has an activation energy of 1 eV and goes down about 1.5 eV. So that's the reaction. This is a classical exothermic reaction. It's clear what's going to happen. You can just look at those molecules. You can see that the product in the transition state occupy less volume than the reactant. You see that? So that means that both of those are going, as you apply pressure, you're going to favor the thing which occupies least volume. So both the activation energy and the exothermicity or exoenthalpicity will be increase, and that's what you see. But we can actually calculate the reaction profile for these reactions, and that has been a lot of fun. I do want to go on to really get at what I wanted to tell you about, which is what sense can we make of the structures that we see under extreme conditions. There are some reviews here if you need to look up about the structures of the elements. Much of what we know about hydrides comes from the work of Eva Zurek and her able co-workers at Buffalo University. And this is summarized in 3 reviews here. My opinion is we do not have yet any rules for deciding which stoichiometries will be stable or metastable. But we have reasonably reliable methods for calculating their stability. And maybe we have ways of talking about the structural motifs observed. That's what I want to talk to you about. And perhaps we have pieces of an understanding of how these bonding motifs vary with hydrogen ratio and pressure. But overall, we can calculate, but we don't understand. That's a very interesting philosophical situation. And it's related to something I've written with Jean-Paul Malrieux about a general struggle in model times between simulation and understanding. And if you are interested in these philosophical questions, you can read a little more about it. At 1 atmosphere, normal valence rule apply to hydrides. You would not expect for lithium hydrides anything else than LiH, because the valence of lithium is 1, and so is the valence of hydrogen. Well, there are some interesting modifications of that. You would not expect for calcium and hydrogen anything but calcium H2. But it's clear that all the rules are off under high pressure. And it's interesting. Some of the things that you can get even in 1 atmosphere are interesting. For instance, I don't think many people knew that you can get, here's the most hydrogen-rich compound at 1 atmosphere. It's barium-rhenium H9. I've defined hydrogen-rich here by atomic ratio, not by mole ratio, not by weight ratio in any kind. So there are 9 hydrogens. Normal valences, barium, rhenium H9 has a rhenium H9 2- ion, which if you like has a 9 H minuses, a rhenium +7. Rhenium is under manganese in the periodic table. That's a 2- ion, rhenium H9 2-. And we actually know the hydrogens from positions from a neutron structure, and there is a barium 2+ to balance it. Incidentally, the hydrogen density of this material, now in terms of grams hydrogen per liter of this stuff, is 132 grams of hydrogen, which is twice that of liquid hydrogen. You can see why the hydrogen economy people are interested in these, why there is interest in storing hydrogen is, and that will come back to something. One thing that should be clear is there is close to 0 experimental evidence on the structure of the high pressure polyhydrides or superhydrides. And I mean on where the hydrogens are located in them. The reason is that X-ray diffraction is weak and the neutron structures are hard to arrange. And we heard Raini talk about this last week. At times one can observe the hydrogen vibron, distinctively high in frequency and a diagnostic of H2. The field relies on theory. I'm not going to say anything bad about my folk, except what you see here. If I see a theoretical paper that gives 4 significant figures after the calculation of an enthalpy, I stop reading that paper. That person has no concept of what theory can or cannot give. Stoichiometries we know from theory at elevated pressures, and this comes from one of these reviews of Eva's, are varied. For lithium, they range from lithium rich as lithium 9H, to hydrogen rich. I already mentioned LiH to LiH6. And these are the things that I say we cannot predict. But what do we see in them? We see in these H2, maybe an H2 that's negatively charged. There's a construct. We do see H3-, a linear H3-, and we'll talk about that. These are things, these are in the alkali metal and alkaline earth hydrides, and even in the trivalent ones like scandium and yttrium. These are generally hydrogen in the environment of an electropositive metal, so that the electrons are given up to the hydrogen. The polarity in lithium hydride is definitely lithium plus, hydrogen minus. The electron affinity of hydrogen is not big. It's slightly less than EV. But under pressure, it's certainly possible to transfer electrons to hydrogen. H minus, if it were formed, forms only a weak complex with H2. Essentially, the H minus stays 2.8 angstroms away from an essentially unperturbed H2 to give a charged quadrupole complex. The linear triatomic is a saddle point, a transition state about half an EV above H minus plus H2. But it's definitely formed in extended structures. We'll see some of those. This might amuse, just sort of amusing. We tried to stabilize H3 minus at 1 atmosphere. How would you stabilize something which is a saddle point? Well, obviously, since it's minus, you got to attach some positive things to it. So we put a lithium at each end. You see it here. And in fact, this was bound, barely bound. The 2 lithium pluses and an H3 minus, but it's a model for what it could be in a solid state. One of the amusing things is once you look at the distance, lithium to hydrogen, in this equilibrium state, it's 1.66, which is just 600ths longer than in lithium hydride diatomic. So there is a rather amusing, totally different way of looking at Li, 2 Li pluses stabilizing in H3 minus, and that is to see it as 2 LiHs stabilizing in H plus. It's good to have alternative ways of looking around this. It's the same thing. It's a cation. It's just a dipole charge complex versus a quadrupole 2 charges complex. So it's not that different. In the solid state, Zurich's group has found a variety of structures with H3s. You can see them. They have even found the normal modes of vibration in the calculated in the various the phonon modes that correspond to a symmetric or an asymmetric stretch of these. The H3 minuses are definitely there in the extended structures. And as you get more hydrogen, you get further aggregation. Okay, now I want to see, are there things in chemistry at 1 atmosphere which are like that? So the first thing, and I do fault the high pressure community for this, for 35 years, we have had molecules in which H2 has been complex to metal atoms. These are not new, and there are hundreds of them. Well, not many hundreds, maybe 600. They were first made 35 years ago, and in these, remember, H2 is H2. It appears in a gas, it appears in a molecule, it appears as a solid at various pressures. You're not going to make something else out of it. So you better pay attention to it when you see it in a molecule. And that's what the high pressure community did not do for these complexes. Because the distances here are available, because most of those 500 structures have had neutron structures. And you can also get from NMR coupling constants, you can get a distance. And some of them are almost unperturbed, and some are stretched as long as 1.3 angstroms for the HH distance. So you have a range of these compounds. Look at these neutron diffraction pictures that you see at the bottom here. Some of them are complexes also where you have both H2 and, as you see in the one at right here, both H2 and 2 hydrides by themselves. So they're hydrogen in different forms. These are around, and it's interesting to see a connection between them and the organometallic ones. The other piece of standard chemistry that the high pressure community working on hydrogen has ignored is the metal hydrides that I told you are of interest to people because of the hydrogen economy. Look, these have been around forever. And so people have studied, how does hydrogen get into nickel when you expose it, or into platinum? And they know a good bit from kinetics and from surface studies, surface chemistry at low pressures. And what is thought to happen in step 0 here is that first you have to get the surface clean. The reason you can cook in aluminum pots is your aluminum pots are covered with a rock-stable aluminum oxide layer that protects them from anything, but you better not scratch them too hard because you will expose the aluminum, which will react with the iron on the stove. So that, anyway, you have to first clean off the surface. You high temperature and pressure, sinter the particles, break the oxide layer. The next thing that happens is chemisorption of H2 on the surface. The next thing that's likely to happen is electron transfer from the surface to H2 to make H2 with a partial negative charge. We've calculated around 1.4, the HH bond breaks. At that point, you have H minus on the surface. You see different geometries for a drawn, and these are not my drawings. These are one of thousands of such drawings in the metal hydride literature. And then the hydride migrates inside the surface to give the metal hydride. There's a lot of room between the metal atoms. Anyway, this is a literature which is there, just waiting to be connected up to the metal hydride story. There's a story around polyhalides and polyiodides. Now, you wonder, what is the connection between molecules that contain bromide, chloride, fluoride, iodide? Well, look at fluoride. Fluoride, F minus, is isoelectronic with neon. It's got a filled 2s and 2p shell, right? Fluorine is F minus. We'll have 2s squared, 2p6. Well, hydrogen has a filled 1s shell. So H minus is electronically like fluoride. Turns out they're about the same size. That is not an obvious thing. But I can put it to you crystallochemically in the following way. If you look at the crystal structure of lithium fluoride and lithium hydride, where I've substituted fluoride for hydride, they have the same lattice constant about. So that's telling you, if the lithium is a certain size, that the hydrogen and fluorine are also the same, similar size. It's in a rock salt structure. The halogens, X2, fluorine, chlorine, and bromine, all have an interaction that is bonding with an X minus to give a trihalide, which is a linear molecule, as you see shown here at left. And these linear molecules are bound for fluorine by 48 kilocalories. I'm sorry for the mixed units here. EV, kilocalories, and kilojoules. That's the reality of the chemistry world, as we have to move between these. These linear things are bound. They come unsymmetrical, they come symmetrical. There are hundreds of these iodides. Not only are the trihalogens bound, I want you to connect this obviously to H3 minus that I just showed you. That is, this is just like H minus plus H2 gives H3 minus, except it doesn't happen in 1 atmosphere, but happens in a solid at higher pressure. Here it's happening at 1 atmosphere for halogens, but it's a similar story. It's also a similar story on a level of bonding. Here, not only do you form I3 minus, but you form polyhalides. These are polyiodides that are there in the old-fashioned iodine that we used to get on our cuts in old time in Germany and in New Zealand as well, probably. They are various structures of this type, not only for, they also happen for bromide. Here, there are fewer of them, but they happen for other polyhalogens. What I want to do is I want to connect these up to the networks that are seen in these calculations. These are very much, networks of hydrogen are very much like the networks of iodine that you see over here. So that one can get an inspiration. I would say today that if anybody who is searching for structures finds as weird a structure as you can imagine, you would be making a serious mistake if you didn't go to your neighborhood inorganic chemist and ask them, have you seen anything like this? Because the chances are they have. And that is, it's not only useful, it's intellectually satisfying. The world is connected up, and that's the connection that we're forming here. Alkali metal halides, also, this is a province which Oganov has done lots of calculations, though Zurich's group has done some as well. But you see things like NaCl7, Na3Cl. In these, there are also trihalide units. So even though we don't have any rules, I'm going to tell you how to sort of come to peace with seeing a trihalide. Let's look at an example. I have some rules written down, but it's easier if we look at an example. Take NaCl3. How am I going, it's in blue here. How am I going to come to peace with NaCl3 when I know that NaCl is the normal ionic compound? Here is how I do it. First, I double the structure. Why do I double the structure to Na2Cl6? The reason is I don't like odd numbers, okay? It's a weird reason. Nature does what it wants to do. I'll write it as Na2Cl6. Now I write it, I pair up the chlorines as chlorine molecules. Why do I do that? Because I know that chlorine molecules like to form by 35 kilocalories per mole. So I write it now as Na2 and 3 chlorine molecules. Next, I transfer 2 electrons from the sodium to one of the chlorine molecules. You see that? Now I have a Cl2 minus. Cl2 minus is a very unhappy beast. In a Coulomb explosion, it goes to 2 Cl minuses. Na plus taken twice, 2 Cl minus. A Cl minus next to a Cl2. Hey, I've seen that before. That's formed a trichloride. So I have an Na plus taken twice and 2 trichlorides, which are those polytrihalide complexes. I like this, but I don't claim prediction. I've just come up with a way to think about it. There's nothing original about this. Artem and his group have thought about this in a similar way, and Eva and her group have thought about this in a similar way. It's just a way of thinking. What happens, incidentally, if you have something that's metal rich? What if you have sodium 7Cl? How are you going to think about sodium 7Cl? Well, turns out that there are interesting molecules called Swiss cheese metals. You'll see why they're called that in a moment. Materials of the type of cesium-7O, rubidium-9O2. These are all at 1 atmosphere. And in these, what happens is there are little ionic fragments like an oxygen that's octahedrally surrounded by cesiums. But really, the way to think about it is that oxygen really can only go to 2-. Look at cesium-7O. The oxygen goes to 2-. 2 of the 7 cesiums go to +1 each. 5 of the cesiums remain as they are, cesium atoms. And then the structure is built of an ionic piece surrounded by metal atoms in there that form a 3-dimensional network. Here they are in another way, a little ionic hole in an otherwise metallic structure. Many of these are electrides, actually. Some of them, they're all metallic, and to date, none of them are good superconductors. But maybe that'll change with time. I actually think they're worth looking at. So they are part of the story. So there are ways to look at this. There is more about a specific way, but I want to actually move. There are more things I wanted to tell you, but I don't have time. I wanted to talk a little bit about the various hydrogen polyhedra here, and where to draw the bonds in them, and is it better to draw the polyhedra as you see at upper left here in a sodalite polyhedron in scandium H6, or should one draw these as clusters, as networks with sharing with metal to hydrogen bonding? It's something we can talk about, and you could ask me about. I wanted also to tell you a little bit about superconductivity. It's all negative in a sense. If I see another Macmillan equation in the next paper, I'm tired of seeing them without any understanding. I want to go beyond that. I think we can go beyond that. I think we lack an understanding, both physical and chemical, of superconductivity, even as we can calculate TCs. And what I mean by an understanding is that even given a stoichiometry in a structure, we cannot qualitatively, without calculation, say whether it'll have a high or low TC. And you know, here are these two networks at left, one in LH10, the other one in the calcium H6 and scandium H6 superconducting. To say that the polyhedra in here are responsible for the superconductivity of these solids is about as informative to me as saying that at 1 atmosphere, if I look at a rock salt structure, here you see it, that the octahedron of chlorines around a sodium is responsible for the ionic character of NaCl. These are observations of structure. Please, please don't endow them with causality. There is nothing in this that you could take over to the next molecule. You can make a loose association that you see these, but then in some others you don't see them. You don't see the polyhedra. So I would be a little hesitant on this. I think we could get more, and there are more questions that we could ask to get at what is involved in electron-phonon coupling. And you could ask me about that. I'm not the only one who thinks this. Here is from a paper by Pickard, Araya, and Arametz, 3 people active in superconductivity, in Annual Review of Condensed Matter Physics last year, plotted out TC versus the pressure for the superconducting materials, which includes both the ones at P equals 1 atmosphere, and every blue point here is a calculated one, and only 2 of these have been met of course, the people who have worked with these are enthusiastic that theory has supported the structure, and theory has played a certain important part throughout their experimental search. But be critical about this. I think this is a correct statement. An enduring puzzle is the disparity between the number of theoretically predicted superconductors that now populate the literature and the few that have been experimentally observed. As mentioned above, and it talks about the reasons. The reason I mentioned Bernd Matthias in a section, at the end of my abstract is that the outlook that I am giving to you here is one that I think Matthias died 40 years ago. So there are very, very few of those here who knew Matthias or who have heard him speak and knew his personality. But he was supremely critical, and he was supremely skeptical about theory in particular. And he was a master of finding superconductors. And a very special person, and I urge you to read about him and to read some of his talks, which have been recorded. I would like to channel Bernd Matthias in that skepticism, as I've tried by raising these questions. Brief summary: exercise skepticism, especially on your own work. That's the hardest thing to do. To be skeptical of other people's work is trivial. To be skeptical about your own work is hard. This is where research group meetings help, if people speak up freely. Avoid hype. That's tough in an age of science and nature, and editors and the press agents for your university, but you can do it. Give credit. Excess credit never hurt. Less than adequate credit always hurts. Your reputation, I'm talking about. So that they give credit, it doesn't hurt. And the last thing is this philosophical thing is, I don't think numbers are understanding. I think understanding is something much more than just getting the numbers right. And I urge you to look for that in the work. Thank you very much.
Thanks, Roald, for a provocative but very valuable talk. I'm sure there will be questions for Roald, so please speak up or use the chat box.
Hi, Roald. This is Shanti. Very inspiring talk. Thank you so much for the review of all these interesting concepts. One question I have about these polyhydrides and generally hydride materials is the presence of hydrogen, which is creating this nuclear zero-point motion that can affect the stable structures. So, and I think, I mean, do you have any comment about that? I mean, for looking around the, I mean, I know this is not theoretically done very much, but it always worries me, especially when as an experimentalist, people look at the, using like neutrons, they look at the structure of something with deuterium replaced with hydrogen that has double the mass. And they assume this is going to be exactly the same structure. So how would we look at that?
I think the people who do neutron structures have ways of probing this. I think the availability of deuterium is itself, of course, a tool for both, in every kind of spectroscopy, like vibrational spectroscopy or Raman, but also in isotope effects within a BCS theory for probing the mechanism if vibrations are involved. The 0-point vibrations have been a problem for theory, how to include them or not. Obviously, people try to avoid including them if they can, but they do if they're pushed or if they see that it's necessary. And we can see some good examples, for instance, in the H3S story of including 0-point vibrations in the calculations.
Yeah, in that story, I think it was mentioned that without, if I read it right, that without including the 0-point effect, we cannot stabilize some of this, the structure, yeah.
And the transition between the highly symmetrical IM3 bar M and the lower symmetry, the R structure, is strongly affected by 0-point motions. And I like that. I don't have enough experimental abilities to be able to say anything more about this.
Thank you.
Maybe somebody else can.
Thank you.
So I had a comment and a question. It's Eva. Hello, everybody. It's really good to see everybody. I just wanted to say that in this area of not seeing people. So first my comment, actually, Roald, you talked about Kubas bonding, and this was actually something that Russ observed first in some of these systems. So Russ's group, they synthesized calcium H4, and he asked me to help out with the calculations. And what he realized was that the calcium was surrounded side-on by H2, and because of that, you could have this type of Kubas bonding, and that the Kubas bonding could be important in the chemical precompression mechanism. So that was studied in one of Russ's papers and my paper, and Tianga is actually looking at that for a number of different structures computationally. So that was one comment. And then another question I had is, you've touched on a lot of the problems that we have as computational people in trying to, come across guidelines of what structures to consider more for properties calculations. Like, we have all of these structures that we make and in our computations, and which ones do we analyze, which ones are important. So those are many issues that my group is facing in deciding what to consider further. But another issue that I don't have any feeling for right now is which ones of those structures are synthesizable without even taking a look at the potential for reactivity. Can we guess anything about that? Can knowledge, I think that even at 1 atmosphere, there have been studies on databases and on enthalpy criteria of how unstable things are, and it's not quite well known how you can describe things that are synthesizable versus ones that are not. Have we not synthesized them, or is it just inherently not possible?
Yeah.
Yeah.
So it's so one of those papers that you showed to me, the one from Cedar and Hautier from the Materials Genome Project, recognizes the importance of metastability and tries to, but then it tries to address it with essentially massive data handling, and another one of the papers tries very interestingly to put a kind of chronological basis for this. I think one just has to talk to good solid state chemists about what is synthesizable or not. Frank DeSalvo, when he was active, or Bob Cava, or Jim Corbett when he was alive, John Corbett when he was alive, were the people I went to ask them, is this realistic? Bob Cava, of course, is still very active. And it's very hard to make general predictions, but some general knowledge is important. Let's take lithium chemistry. Some of the kinds of compounds which are lithium rich are just not going to have much stability. Now I'm thinking about chemical, they'll be very reactive chemically. I know lithium chemistry, and I have hardly ever seen a lithium that does not get its hands on electrons nearby. The classical lithium compounds we see are always with Lewis base connected to the lithium, typically oxygen or nitrogen. And so those are the ways to stabilize them. There are interesting exceptions like gold chemistry, but anyway, some knowledge of chemistry will help to see if there is a chance of returning the material to 1 atmosphere. I don't have any good guides here on this.
Oh, thank you. Actually, what you said was useful.
Thanks, Eva. More questions? Since you kind of rushed through the polyhydride discussion at the end, it's perhaps useful to point out that in those structures, which we're very excited about, actually also there's nothing new under the sun. These structures are known in zeolites, in aluminum silicates.
Yes.
And that was not pointed out early on in the discovery of these materials.
That's right. Yeah. And the other zeolites, the zeolite story is just amazing. And it has itself several interesting chapters. First in the zeolites as inorganic materials, and then in clathrates rather, as the classical clathrates like the water clathrates that binds methane. But then there are the clathrates which have which are made of silicon, let's say, and which have a barium or something else in the middle of the polyhedron. Those structures, the story of the discovery of the clathrates is remarkable and worth telling by itself. I have another seminar about those. And I now believe I can teach somebody to love clathrate structures. That is, I can make sense of them in some way. But yes, they are quite incredible. Yeah. So when should we draw the lines from between the hydrogens, from the metal to the hydrogen? One of the things we don't draw is one of the things I was talking about in that section was about using histograms, which is what I'm addicted to. And the most simplest thing, using a listing of the distances to allow you to decide what is bonded to something else without going into a discussion of the bonding. And another time I'll talk about that.
Very good. More questions?
I have a question.
Go ahead, Ryan.
Yeah. Russ, you hear me?
Yes, Rainey.
Well, what an absolutely fantastic talk. I'm really blown away by it. Your last slide should be posted by every journal we publish in. And I have a question to you. You mentioned the stability of nitrogen. Some years ago, we actually did, this highly stable material. I mean, you probably know it. Years ago, we broke that bond just by pressure and temperature. The question is to you, why cannot we stabilize it? Why can we not recover it? This is a chemical or you would expect that the barrier is huge and that it should be very easy to recover like diamond. Any thoughts on this?
So you're talking about, let's say, the cubic gauche structure of nitrogen, or one of those high pressure forms of nitrogen.
Yes.
Which is in structural detail to a chemist a 3-coordinate net resembling closely the nets that one finds in the elemental structures of arsenic and antimony. Phosphorus chooses its own way, though there are some forms of. So why can one not recover that 3-coordinate nitrogen? So I think I think the main factor is that the barrier to falling apart to N2s, it's not the driving force, because the difference in enthalpy is not that great between the diatomic and the singly bonded form. But that still the dinitrogen is more stable, and the process of falling apart from the 3-coordinate structure to many N2 molecules is what we would call in an organic chemistry context an allowed reaction. It's a reaction that doesn't face any electronic barriers. And so the same thing that makes that 3-coordinate nitrogen structure fall apart into N2 molecules is the same thing that makes the diatomic P2 fall into the 3-coordinate structure. It's just that the enthalpy has changed greatly. You can ask me, why are multiple bonds something of the first row of carbon, nitrogen, and such? We could talk about that. The other thing that could be possible is that the 3-coordinate net that you are describing for nitrogen is very reactive. But then one should be able, I know in what way it would be reactive. It would be a super base. So one has to keep away acid media. So one has to open that high pressure cell in the presence of a lot of base, hydroxide or anything like that. But you have tried to open those things under rare gas atmospheres probably, and you still couldn't get anything except N2, I'm guessing.
Right.
Okay, I was thinking out loud.
Thanks. More questions?
Well, I have one last question, just to make things more of a comment to more complex to what you already described about the effect of metastability, reactivity, all these things. How about the effect of the stress? I mean, not uniform stress, non-uniform stress, basically, on these chemical reactions, that they may prefer one structure. Is there any comments? Because that happens in experiments all the time. We don't see it maybe in theory it's easy to relax the structure, but in experiment, we often expose the samples to uniaxial stress from between one experiment to another. That's done between different groups. So the comparison.
Someone mentioned to me a set of experiments with the diamond anvil cell was stressed while the pressure was applied by being rotated. Do any of you remember such experiments by somebody?
The torsion, I think, the anvil says that they rotate the anvils.
Yes. Is that something that's used to go through, to help things go through phase transitions? I don't know.
Yes, that's absolutely true. Yeah, we had a talk in this series on this
Yes.
earlier. Yes.
Yeah.
It also simply destabilizes the reactants, so you can lower the effective transition pressure by making them defective.
Yes.
Raising the free energy.
It was a talk.
Yeah.
Remind us of the name of the person who gave the talk. If you...
So can we theoretically do the same thing with the structures to see if we can produce a little bit broader phase space?
Mhm. I don't know. We'll talk to Eva.
Yeah.
Okay, if there are no more questions, thank you, Roald, for a terrific talk. I heard you volunteer to give at least 2 more, so we'll have you back very soon. But next week, we will take a break so as not to compete with the inauguration of our new president and any events that may surround that inauguration. So we'll see you in 2 weeks. Again, lots of comments in the chat box. Wonderful talk, Roald. Thank you so much.